Today I'm going to talk about my slice of the RCCI work, and so it's a big pie, and part of it is decoding the tree rings. So we have samples taken from trees at all sites, and the basis is dendrochronology, and so dendrochronology is the dating and study of annual rings in trees. And we can see that a tree is putting on a growth ring every growing season, and I want to point out the variation in ring width. And so we could see some smaller rings and some larger rings throughout this span. And so my goal is to put a precise calendar year on each of these rings. And the width of these rings depends on the surrounding environmental and climatic conditions. And so what Healy just spoke to, those extremes, are driving this pattern. So to put a precise date on each of these rings, we have to rely on the principle of cross-dating. And so this is using the relative pattern of ring widths across a sample population of trees. So we can see in these examples we have three cores, and we have different absolute values of ring widths, and we have similar relative patterns. We have 1950 marked, every decade is marked, and you can see in the 40s there's a fingerprint, which allows us to date each ring precisely. So it's important to cross-date because we could have missing or locally absent rings. We have an image here of Marie taking a core sample. We do this with an increment borer. So this is an auger-like instrument which is screwed into the tree, and out comes a tree core. It's about the width of a pencil. It could be 24 to 36 inches long. And so if we took a core sample from the tree here, we'd capture every growth ring. However, look down here, if we took a sample here, we'd miss this ring, it'd be locally absent. So the tree isn't producing wood during this year. So we use the principle of cross-dating. We have one core here, a second core here. We use the relative patterns and we lock in this year and put a ring there. So that's cross-dating in action. So let's look at how a tree grows. In this image, if you could stack each one of these on top of each other, we'll get a tree growing over time. So I just want to point out that as a tree grows, wood is produced from the cambium, and this is a layer around the tree. And so this is the total volume produced, and this is something that Steve Sillett's going to speak to. I'm looking at the plane here. You can imagine tree cores being taken, and so I'm looking at this radial plane, and I'm looking at the year-to-year variation of these ring widths. So, with cross-dating, we can take cores from live trees, have the outermost ring anchored, date of sampling, overlap patterns of marker years. Marker years are consistently small or larger rings that hold constant among a population of sample trees, and we can create a time series or chronology based on these ring widths. Once we can create these chronologies, there's many applications of dendrochronology. I'm going to speak to creating these chronologies and the interannual variation in the ring widths. Steve Sillett is going to speak to tree ages and volume growth histories of the RCCI study trees. We can do isotopic analysis of these particular rings as each piece of wood that's laid down captures a chemical signature that we can investigate, and Todd Dawson and Anthony Ambrose can speak to that. We can capture extreme climatic events. We can date these way back in history. We can capture fire scars. If we have a chronology, all these rings are dated here. We have fire scars. We can place years of fire events, create fire histories. This picture shows tree core samples taken from the Officers Club at the Presidio. So we're working with a dendrochronologist from the Oxford Tree Ring Lab who's taking these samples, and he's using the redwood chronologies created for RCCI research to date the buildings at the Officers Club. So there's a vast range of applications, but we need to create the chronologies is the first step. So we have giant sequoia forests and coast redwood forests as a focus of RCCI research. We have core samples taken from our study trees. And from a dendrochronology standpoint, this is a tale of two trees. Giant sequoia is one of the species that is the cornerstone of modern dendrochronology. So in the early 1900s, as A.E. Douglas was formulating these principles based out of Arizona, giant sequoia was a species that he relied on heavily. On the other hand, coast redwood has remained tenuous in the creation of chronologies at all. They have not been cross-dated across the range to any long-term extent up until now. So here we have, this is A.E. Douglas, and we have a sample in the giant sequoia forest being taken in 1931. And so at this point in time, chronologies were made for giant sequoia that are over 3,000 years old. And the giant sequoia tree rings are somewhat consistent with strong marker years every 50 years or so. So they're a wonderful tree to work with and helped solidify a lot of the principles of dendrochronology. Here's an image of coast redwood. So coast redwood was sampled in the 1920s, a little after Save the Redwoods and those images that Emily showed. And rather than cross-dating these species, it was simply documented how complicated the series were and unsuccessful attempts at cross-dating. And so we could see with this image some of the reasons why. So you can see here where the rings pinch out here. And so we have 3 rings here. If we took a sample, a core sample here, we'd capture these rings. If we took one below, we would have locally absent rings. So that's called wedging or discontinuous rings. So around the circumference of the tree, you wouldn't be able to, that ring wouldn't go all the way around. So this was documented early on. We also have tight rings. You could see the width of a penny and the dozens of rings that would fit in this span. So these are some growth characteristics that make redwood particularly difficult to simply put those calendar years on. Hope you can see this. Might be a little washed out, but we have someone standing here against a tall redwood tree. What I want to point out, there's been some piecemeal progress made in accessing the record of coast redwood, the tree ring record. In 1940, Edmund Schulman, who is also a founder of dendrochronology, he was Douglas's student. He looked at Douglas's collections and he discerned an intelligible record. So there's something there. These trees are picking up the surrounding environmental climatic conditions in their ring widths. He noted that from his samples, which were down trees, he noted that samples higher up on the trunk from codominant or dominant trees provided better access to these tree ring series. In the 90s, Peter Brown and Tom Swettenham did some great work doing fire histories in Prairie Creek State Park, and they did create a chronology back to 1750 for a fire history, and that was based also on down trees. But for our CCI research, and we want to get an idea of what's going on with these trees in these particular forest plots, living trees, we want to access living trees. And so it's really been a combination of technical expertise and support from donors and through Save the Redwoods League and access to these forests that we have been able to get the replication and the cores necessary to finally create chronologies for coast redwood. And as well, we've done this for giant sequoia, and this is linked to many other aspects of our CCI research. Again, you've seen this map here. So these are our collection sites, which you've seen. We have the rainforest sites in the north, all the way down to the Big Sur for coast redwood. Giant sequoia range is here. Okay, so we have researchers in the trees taking core samples. This is Jim taking a core sample. And so our strategy for core collection is to take samples at regular height intervals along the tree, along the trunk of the tree, and at multiple positions. So we have a high within tree replication. Lowest sample is above the buttressing, the abnormal buttressing. Okay, so we get these core samples carefully taken from the tree, bring them back into the lab, and I will put them on these wooden core mounts, sand the cores, and we can see the tree rings revealed. And so what I'll do is take the cores from each individual tree and look for these marker years. So I'll cross-date on a tree level and then look at those series between each other. You can see we have a lot of missing rings here for coast redwood. And you can see some marker years noted. For each series, we measure, scan it in, get ring widths. And so this is a time series of ring widths. 1,000 microns is about a millimeter. And I believe that's 1983, which Healy pointed out as an extreme precipitation year, and down to some of the droughts here in the 20s. We can run these series with each other, and so we can have software to help us get correlations and confirm our cross-dating. So for giant sequoia, what did we find? How did these tree rings look? They both lived up to their reputation. Giant sequoia rings were very consistent, and we had strong marker years every 50 years or so. Wonderfully fun to work with. Coast redwood, very difficult. So this was quite the task and took a lot of dedication to get these series done. We had the usual suspects. So these are images from tree cores, and just in these simple cores, we can see wedging and discontinuous rings showing themselves. These were almost always associated with missing and locally absent rings. We have a spiral compression wood pattern, which was noted early in the 20s, and this makes cross-dating even more difficult as you're looking for year-to-year variation with this larger variation occurring. We have fire scars, which we find in giant sequoia as well. Coast redwood adds another layer of complication. Tight rings. This is taken from a 4-inch span core with over 300 years in there. So we have some samples set out later, put them under the microscope, and you could see what I deal with. Okay, nevertheless, we were able to find consistent, strong marker years for both species. This was very exciting. There is a signal in coast redwood, and we can access it. We have. And so here we can see some marker years in blue. We can see cross-dating here. We placed 3 rings in this region, marker years on either side. We had some regions where it was so tight, there was so many missing rings, 20 in this span here. This is still good data. We know the number of years and the total distance of wood on this radial plane produced. And sometimes cross-dating would end. We can get percentages of cross-dating based on this. So I have for the 500,000 tree rings that we've measured, everyone is coded in this way so that it can be used for RCCI and future researchers. Say we want to go and do isotope work, we know what they're coded as. And so this catalog is to be built upon and used. This is an example of what the marker years would look like. Let's focus over here. So we see, I also used late wood as a marker. So we see 1936 has a thick late wood, and so does 1934. They're both big, thick late wood, and 1935 is a small ring. So not only would I go for one marker year, I would go for a fingerprint or a pattern of multiple marker years. And so for coast redwood, this would have to be done almost every decade to create these fingerprints in order to slowly inch back the centuries and millennium that we've covered. And so you can see for different trees at one site, I've listed marker years, and we have coherency across trees. So it's a common signal. So you can see blue years are larger. This one's associated with the El Nino year, and we can see red years are smaller. In total, we successfully cross-dated these species, these trees for our sites. We can see the sites, total number of trees, 76 for coast redwood, 44 for giant sequoia, over 1,500 series. So a core goes in, if it goes beyond the pith, that's another series. As I had mentioned, we have nearly 500,000 rings quantified. Our oldest core for coast redwood goes back to the year 328, 474 for giant sequoia. So cross-dating. Out of all these rings for giant sequoia, 99.5% of them were placed with annual resolution. For coast redwood, not too shabby, 84.9% were placed. We had a lot of missing rings. 4.4 of them were locally absent at that position on the tree, compared to 0.2 for coast giant sequoia. So let's look at each tree. Let's look at the tree level of cross-dating giant sequoia tree. Within each tree, we had a high percentage for each tree, we had a high percentage of cross-dating. So 90% of the rings was the lowest, and that was for a suppressed tree. I want to point out for coast redwood, we had a wider range of variability looking at which tree we sampled. And our lowest was about 4%. So we wanted to ask what caused that range of variability. We came up with a few clear trends. The spiral compression wood it was of course more difficult. Interestingly, the the 9 trees where we show spiral compression wood were all located in northern sites. It has been observed elsewhere. And we have suppressed trees. We're confirming the findings of Edmund Schulman. Indeed, suppressed trees are more difficult to access these tree ring years. So now within the tree, again with giant sequoia, within any given tree, one core was pretty good. Coast redwood was quite variable. So we looked at how did this compare along the trunk. We found that the cores taken closer to the base were 10% less successful, and this is above the abnormal buttressing, and even still we're able to pick up this trend. But the main point is the high within tree replication that this team was able to access has allowed for this code to be cracked. Here's an example of a chronology. So what do we do once we have these 1,500 series? So we can create chronologies. These are site chronologies. So you can think of this as a ruler or baseline upon which we can go in and measure other tree core samples. This is showing interannual or year-to-year variability. For this chronology, the long-term trend has been taken out. That will be addressed elsewhere in the symposium and standardized around an index of 1. Okay, so in blue we have the number of trees, in red we have the number of series. The top dashed line is potential series if we cross-stated every ring. The solid is actual series. Where there's a discrepancy, larger, we can see it's more difficult cross-stating. So we're coded this way to go in and improve our chronologies. We can see replication does drop, and so we will be needing to improve these chronologies. They're meant to be working chronologies. Zoomed in, we can see now we can access this year-to-year variability. 1983, 20 is our droughts, 83 is El Nino. So we can see that the trees are indeed picking up the climatic signal surrounding them. The potential of this is large. Here's our chronology lengths. Coast redwoods in green, giant sequoias in blue. Our oldest chronology is from Coast Redwood, 328 from Redwood National Park. After that, giant sequoia chronologies are quite long, most over 1,000 years. For Coast Redwood, we have some shorter because the trees in the forest were not as old. Fortunately, now that we have these chronologies created, we can use remnant or downed wood. So one reason that Coast Redwood and giant sequoia have such great potential for dendrochronology is their decay-resistant heartwood preserves that wood. So if we go in the forest and can take remnant samples, they can overlap and we can cross-date back in time, extending chronologies beyond the age of the oldest living trees. And we've already started to do that, and interestingly, at this lower site that we need replication on. Okay, so here's Jedediah Smith Redwood State Park. This is our northernmost site for Coast Redwood. And I want to point out this marker year in 1739. You can see it's the smallest ring width for the entire Coast Redwood sites. Here's the actual tree rings. So here we're progressing. This is 1738, and we have a growth reduction in 1739. So I found this interesting because years ago I was working on creating a chronology for Port Orford cedar. This is a species which grows in southern Oregon, northern California, whose roots are in rivers and stream systems. And at that point in time, we had documented damage to this 1739 ring, which was consistent. We sampled across its range. And so what we're pointing to here is a regional extreme climatic event, most likely associated with freezing. We can see 1739 exemplified in the tree cores. So here we go, bounded by marker years, and we can see that signal. So this was great for me. For the northern sites, which were pretty difficult, I could look at them and find that pattern and pretty much be sure that I was going to find 1739 as a marker. Here's a chronology from giant sequoia, from giant forest. It goes back to 474. Note the tightness of these two red bars showing that we've cross-dated almost every ring. And what I want to point out here is another marker year, 1580. This is the smallest ring width for all giant sequoia chronologies that we sampled. And This was interesting because in 1919, A.E. Douglas made a special collection into the giant sequoia range to simply find more samples that showed this ring. And so similarly, for the coast redwood, I think we're going to need to confirm some of our marker years earlier on. And so 1580 is most likely associated with a year that had an extremely limited growing season. And you can see 1580 just showing up as a small ring here, and it's missing or locally absent in these other series. We can also see fire responses. This is a chronology from Landell's Hill Big Creek Reserve. This is the southernmost of our coast redwood sites. It's on the Big Sur coast. We have a known fire in 1985, and 1985 is this ring right here. We have the response in the following year as the trees are reinvesting into rebuilding their crowns and leaf area. So we can see fire responses as well as fire scars. So we wanted to look at these chronologies compared to each other. So we have the year-to-year variation of the ring widths that is dependent upon overarching climate. How are they similar to each other? And we can see just visually stacking them up, we can see that, for example, 1924 is a consistently small ring among all sampled trees. And as Healy pointed out, we can now match this with historical climate data, such as the PRISM data. 1983 is the El Nino year, and it's a consistently larger ring. So these trees are indeed picking up a signal, and there is synchrony among the chronologies. To take a better look at how the chronologies match with each other, we did a principal components analysis on them. And so this looks at the variation of the interannual chronologies and we see how they load on independent axes. But what you can just focus on is how they cluster in this 3D space. So let's focus on the giant sequoia chronologies. They cluster well together. They're picking up a similar signal. These are all the coast redwood chronologies. There's more of a gradient for the signal that they're tracking. In green, we have the northern rainforest sites. They're very close together, picking up a common signal. And then we have a gradient down to the southernmost coast redwood sites. And the southernmost sites often had higher correlations with their patterns with the coast redwood rather than the the southernmost coast redwood had higher correlations with giant sequoia than the northernmost coast redwood. And so these mid-range ones were a bridge for cross-dating for me, so it helped me see which years were picked up for all sites. So I'd like to point you to my poster where we did an interannual climate sensitivity analysis. So just what Healy was speaking to of the PRISM data, we have temperature, minimum, maximum, precipitation, and we have soil moisture expressed as a drought index. And so what we can do is take each chronology and then relate that to that climate variable. We could see what might be causing the variation in ring widths. And so in the poster we go into detail on that. I'll just point out a couple points. All of our chronologies did pick up summer soil moisture as indicated by drought index as an important variable for their interannual variation. So it's mostly consistent for the giant sequoia chronologies. Again, for coast redwood, we found more of a trend or a gradient. The southern sites showed stronger relationships, and as well, not only in summer, they extended into spring. And so if we just look at all our site chronologies, redwood and giant sequoia, and just their correlation with regional summer drought and California summer drought, we can see that Landell's Hill Big Creek Reserve, which is the southernmost coast redwood site, has by far the strongest relationship with a drought signal. So this is the time series upon which that bar graph is dependent. So we can see in red, we have the Central Coast Drought Index. And so we have smaller years representative of drought years. And in blue, we have the Landell's Hill tree ring chronology. And we can see the tight matching of the ups and downs. So the tree rings are able to capture the drought sensitivity here. So this, first thing, the few times that it drops out is after the known fires where the tree rings lag as they're reinvesting in rebuilding crown and leaf area. So this points to the potential of some of our redwood sites to reconstruct climate. So climate reconstructions are based on a relationship between a climate variable and the tree ring width index. And then you can extrapolate back in time beyond our available climate records. So we can use tree ring widths to look at climate in the past. And the site with the greatest potential at this point looks to be the southernmost redwood site. And we can see that sites at the margins of their ranges are generally more sensitive to climate variation, so they're better able to be a paleo record to pick up that variation. This is a view from the canopy of a tree in the Landell's Hill plot, and you can see how dry it is here. And so definitely able to pick up that drought signal a little bit better. And so I just want to conclude that we were able to cross-state series for all trees in our RCCI plots, which can now be linked with other intensive measurements in these plots, in these forests. And for the first time, we're able to create long-term, well-replicated chronologies for coast redwood across the entire range, which can be used for this and other research. And so thank you. I look forward to talking to you more at the poster session, or if you had any questions now.